Hello everyone, my name is Fred Rispoli and I'm coming to you from Stony Brook University. Today we're going to talk about some examples from Chapter 2 of On's book on probability. In particular, we will go over these 4 parts of Chapter 2, basic probability. We'll look at a few examples. Example 1. Probability using counting formulas, examples 2 and 3. Probability using set operations, example 4. And conditional probability, example 5. Bayes' theorem is also covered in chapter 2, but I'll leave that for a different video. These problems that I've chosen to go over are based on frequently asked questions from students and the results of previous exams. All right, so here's a basic problem. Suppose an integer is randomly chosen from the first 50 positive integers. What's the probability that the integer will be a 2-digit number? Well, we know that in this set of 50 positive integers, there are 41 2-digit numbers. And this would be a list of them. So starting with 10, we get 41. So our probability is the number of elements in this set, which is 41, over our universal set, which has 50 positive integers. So the fraction 41 over 50, converting that to a decimal, we get 0.82. Now it's good to practice some similar problems as we go through this video. So at this point, I would recommend that you stop the video, take a look at the deck of cards that I've displayed here, and try to answer these questions. So from a deck of cards, what's the probability of a one-eyed jack, a king with a sword through its head, also known as the suicide king, a face card, okay, and in part D, we want the probability of a card that's an ace or a club. So stop the video and let's see if you could get these basic probability questions. All right, the solutions are 2 over 52. If you check back, you'll see the jack of spades and the jack of hearts have 2 eyes. Oops, take that back. They have 1 eye. The other jacks have 2 eyes. The king of hearts has a sword going through his head. So the probability here is 1 over 52. Now the face cards, those are the jacks, queens, and kings. And we know there's 4 of these in each different suit. So the total number of face cards is 4 times 3, which gives us 12. And the number of cards that are either a club or an ace is 16. So our probability is 16 over 52. Here you just have to make sure you don't count the ace of clubs twice. Okay, let's look at another situation where it's useful to know probability. This will help us in placing bets, for example. So a good example is to look at horse racing. So suppose that we have 8 horses that enter a race. Question is, how many different ways are there for 3 horses to come in first, second, and third? So order here is important, okay? When you're placing the bets, you must specify the order they come in, okay? This is sometimes called a trifecta bet. So this is where you pick all 3 horses in a race in the correct order, okay? And the probability of a winning outcome will affect sort of the amount that a person gets paid off when they make a bet. Now, a related bet here is what you might call a combination bet. Okay, so here we would want to know how many different ways are there for the three horses to come in first, second, and third without specifying the order. So here the bettor just wants to get correct the horses that finish first, second, and third, but not necessarily choose the order. So again, that's a combination bet. Well, it turns out we could answer these questions using some of the counting formulas that are discussed in Chapter 2. Since order is important, and we have 8 horses entering the race, okay, the number of different ways for the race to finish is given by 8p3. And if we expand that out, that's simply 8 times 7 times 6, which is 336. So if somebody just made a random choice, okay, for the horses first, second, and third, okay, the probability of winning would be 1 over 336. And in this case, a $1 bet should pay off about $336, maybe slightly less than this because the house usually takes a small percentage, but a $1 bet in a fair betting scheme would pay off $336 for this trifecta bet. In the second case, where order is not important, the number of different ways a race can end is given by 8 choose 3 or 8C3. You'll see this notation in the book. So this number is given by, 8 factorial divided by the product of 3 factorial and 5 factorial. When we simplify, we get 56. So the probability that a random choice wins now is 1 over 56, and a $1 bet that wins would pay $56. Okay, here's another problem, and this is right from the Book of On. Suppose a company is hiring 5 people for a position. Of the applicants, 7 are from New Jersey, 8 are from New York, and 5 are from Connecticut. What's the probability that of the 5 people hired, exactly 2 are from New Jersey? So we could define a random variable x as the number of people who are hired from New Jersey, and we're interested in calculating the probability that this x is equal to 2. So we need to count the number of ways we could hire the people. So the number of ways we can choose 7 people from New Jersey is 7 choose 2. Okay, then we have to choose 3 more, okay, and these people will be coming from New York or Connecticut. We're not so interested in, whether it's exactly New York or Connecticut, but we do know that there's 13 other people, okay, that are not from New Jersey. So the number of ways to hire 3 from this group of 13 is 13 choose 3. In the numerator, we have to do both. We have to hire 2 people from New Jersey and 3 other people. And in our denominator, we put the total number of ways to hire 5 people from this group of 20. So we have 20 choose 5. We can work this out, expand these in terms of factorials, then cancel things out and simplify. In the end, we get a decimal 0.387. So that is our probability. Okay, for practice, I suggest that you stop the video and take a look at these 3 practice exercises. The first, we have a student needs to choose courses, 1 each from social sciences, humanities, natural science, and foreign languages. And we know there's 5 social science courses, 4 humanity, 4 natural science, and 3 language courses. How many different ways can a student choose their courses? That's part A. Part B, 4 people are chosen from a 25-member club for president, vice president, secretary, and treasurer. How many ways can this be done? And in C, how many ways can 5 tosses of a coin yield 2 heads and 3 tails? So try stopping this video and let's see how you do. All right, so here are the answers. For part A, we simply use a product rule, 5 times 4 times 4 times 3, so we get 240. For part B, we know we have 25 members, so one way to explain this is to think in terms of 25 ways to identify a president, 24 ways to identify a vice president, and so on. All of these steps must be done, so we need to multiply these. Or we could also think of applying the formula 25p4. In part C, we're looking for the number of different ways to get exactly 2 heads on 5 coin flips. So this would be given by 5 choose 2. And if there were any confusion on it, another way to approach this would be to just make sequences of H's and T's, H for heads, T's for tails, and try to create sequences where there are exactly 2 H's and 3 T's, and you should come up with 10. Okay, so we've talked about probability, just using basic ideas of probability using formulas. Another way to approach probability is using sets, and here we could either work this out with Venn diagrams or we use union and intersection operations. So here's a classic example involving 3 different sets. Suppose we have a group of 160 engineering students. 92 are enrolled in statistics, 63 enrolled in operations research, and 50 are enrolled in physics. And we have some more information. We know 10 of the students are enrolled in all 3 courses. 22 are enrolled in statistics and operations research. So that's the overlap. 25 are enrolled in statistics. 25 enrolled in statistics and physics. That's the overlap. And 29 are enrolled in physics and operations research. So what I would ask you to do here is to begin by filling in the correct number of students in each region of a Venn diagram, and then answer a set of questions based on your solution to the Venn diagram. So part A, we want to know, how many are not enrolled in any course. In part B, the student is selected at random. What's the probability they're enrolled in statistics and operations research, but not physics? C, again, a random selection. What's the probability the student is enrolled only in the statistics course? And D, what's the probability a student is enrolled in exactly 1 class? So with a problem like this, the key is to sort of work from the inside out. Okay, so here you can see I put a 10 in here because there are 10 students enrolled in all three classes. Okay. Now, we were given a certain number of students that are enrolled in statistics and physics. So if we just go back, we'll see over here that there's 25 enrolled in statistics and physics. So I've already counted 10 in the 25, so that means that there's 15 in this region. So this would be the group that are enrolled in statistics and physics, but not operations research. Okay. So you have to be clear that that's sort of the way people approach these problems, and that's sort of the understanding that we have when we look at these. You could see over here, so this sort of oval shape represents students enrolled in operations research and physics. There's 29 of them, but we've already counted 10. Okay, so how do we start filling in the rest of this? Well, if we start over here, let's say in this region, okay, we need to go back and see that there's 22 students enrolled in statistics and operations research, but we already counted 10 of them. So the number of students enrolled in just these two is 22 minus 10, and that's 12. Okay, now you may recall that in the first part of the problem, we were given that there's 92 students enrolled in statistics, okay, but not that 92 includes all of the students sort of in this entire set, okay. So we've already accounted for 12 here, 10 in the overlap of all three, and 15. So I subtract these values from 92, and this tells me that there's 55 students that are taking just statistics. Okay, so we have to do something similar to that to figure out the number of students that take just operations research. So I know there was 63 total taken operations research, but we have to subtract the 12, the 10, and the 19. And so that gives us 22 just in operations research. I know physics has a total of 50. We have to subtract out 15, 10, and 19. So that leaves us 6. And finally, this region outside would be the number out of the original 160 students that do not take any of these courses. So to find this, we'd have to take 160. We could grab all of these with a 92. So 160 minus 92 minus 22 minus 19 minus 6 would give us 21. Okay, so now I have the number of students in each of these 8 regions. So that was the first part of this example. Now, in the next part, we have some questions to ask, and we've done most of the work. So the first question is, how many of the 160 are not enrolled in any course? So that we rewrite off the Venn diagram, that would be 21. If a student selected at random, what's the probability the student is enrolled in advanced statistics and operations research, but not physics? So that would be this region right here. Okay, we have advanced statistics, operations research, but not physics, so I don't want to count this 10. So our answer is 12 divided by the entire number, so 12 over 160. A student selected at random, what's the probability they're enrolled only in the advanced statistics course? So again, this one we can read right off the Venn diagram, so we're interested in this region here. So we get 55 divided by the 160. And the last one, what's the probability a student is enrolled in exactly one class? Okay, so to get this, I need to think the number enrolled in just statistics is 55. The number enrolled in just operations research is 22. And the number enrolled in physics is 6. So we add those up, 55 plus 22 plus 6, and these add up to 83. So our answer is 83 divided by 160. Okay, the last problem we look at is one that illustrates some ideas of conditional probability. All right, so this problem is based on a table, right? Not all conditional probabilities are based on tables, but many of them are, so we'll take a look at one of these. All right, so hot dog eating contests are popular in Brooklyn, really throughout Long Island. I've seen some of them take place in Montauk. They're sort of fun to watch, but I wouldn't want to be in one. Anyway, here we have a table that gives information about BMI, right? That's the body mass index, and age group for a group of adults in a hot dog eating contest at the famous Nathan's. So the first question is just straightforward probability. What's the probability? Person selected at random will have a normal or low BMI. So we're thinking about this column here, and we could read the number off is 0.29. That is not a conditional probability, that's just straightforward probability. Well, with the next question, we do have to work with conditional probability. Let's say that a person selected at random from the group is found to be from the normal or low BMI group. Okay? And we're asking, what's the probability that this person is younger than 30 years old? Okay. So the condition here is that they're from the normal or low BMI group. So I put an A here because we've called this A before. Okay. And we want to find out the probability that they're younger than 30. So our formula for conditional probability, right? The probability B given A is equal to the probability of A intersect B. So A intersect B would be this value right here, 0.09, right? These are the people that have a normal or low BMI and they have an age less than 30. So that becomes the numerator, but now we have to divide by the probability of A, which is 0.29. This was sort of the first part of this example we did a few seconds ago. So you take the probability of the intersection and you divide by the probability of this given condition. So we could work this out and we get 0.31. Okay, just to practice this, once again, I suggest that you stop the video and try to find the probability that given a person is older than 30, he or she is obese. And as a second, find the probability if a person has a normal BMI, he or she is older than 30. Okay, so did you get these answers? The probability a person is obese given they're older than 30. So older than 30 means that we should be looking at this row. Okay, I like to think of this as a a smaller sample space, right? We have this complete sample space, but when we look at conditional probabilities, we're reducing the sample space. So this becomes my new sample space. So we want the probability of obese, given they're older than 30. So this is the probability obese and greater than 30. So 0.28 is our numerator, and then we have to divide by 0.80. So our conditional probability is 0.35. Now in part B, we sort of flip around the role of older than 30. So here the given condition is that a person has a normal BMI. So now the given condition is represented by this column. So the probability older than 30 and a normal BI, this will be 0.20, right? Older than 30 and a normal or low BMI is 0.20. That's my numerator. And the probability of a normal BMI is 0.29. So this is my conditional probability. Okay, so you should keep in mind that for all of these different categories, there are several different types in each category. My goal was not to cover all the different types, but I did go over some problems where I do see some students having some trouble. So hopefully this will help. Thank you for watching. And I will be creating another video, as I said, that covers Bayes' theorem, also in Chapter 2.